Somewhere 1,400 light-years from the chair or bed where you currently rest, there is a world orbiting a gentle, golden star. It is a world that spins through space with an orbit almost identical to Earth's, completing one full year in just 385 days. A world that sits in what scientists call the Goldilocks zone, that precise cosmic sweet spot where liquid water can exist on a planet's surface. Not too hot, not too cold, just right. When NASA's Kepler Space Telescope discovered this planet in 2015, and when the announcement was finally made on July 23rd of that year, the news spread around the entire globe within hours. Scientists were calling it the most Earth-like planet ever found around a sun-like star. Journalists were calling it Earth's twin, Earth's cousin, Earth's long-lost sibling drifting quietly through the constellation Cygnus, waiting patiently to be found. For a brief, luminous moment, humanity let itself dream, and that dream is understandable. It is, perhaps, one of the most deeply human dreams there is. The idea that somewhere out there, beyond the cold, dark veil of space, there is another blue world waiting for us. A spare, a backup, a place where we could start over if everything here went terribly wrong. A cosmic lifeboat painted in the same greens and blues and whites that have cradled every human being who has ever lived and died on this fragile little rock we call home. The planet was designated Kepler-452b. And the dream, as beautiful as it was, began to fracture almost immediately for those willing to look carefully at the numbers. Because Kepler-452b does check an extraordinary number of boxes. The boxes that matter to scientists searching for life, for habitability, for the faint promise of somewhere else. Its orbital period of nearly 385 days places it at approximately 1.046 astronomical units from its host star, which is just slightly farther from its star than Earth is from the Sun. Its host star, Kepler-452, is classified as a G2-type star, the exact same stellar classification as our own Sun. It's roughly the same temperature, roughly the same color, roughly the same mass. When you look at the numbers on paper, you could be forgiven for thinking you were reading the datasheet for the solar system all over again. The planet itself has a radius of approximately 1.63 times that of Earth. Just large enough to be more than Earth, just small enough to still be considered potentially rocky rather than gaseous. Models suggest its mass is somewhere around 5 times that of our own planet, give or take a significant margin of scientific uncertainty. And it sits, as I mentioned, precisely within the optimistic habitable zone of a star that, from a distance of nearly 1,400 light-years, looks unmistakably like our own Sun's older sibling. This is the Earth 2.0 dream in its fullest form. A world that seems, from the outside, to have drawn the same hand from the cosmic deck that Earth drew some 4.5 billion years ago. And for a civilization that has watched its own planet warm, its ice caps shrink, its forests burn, and its oceans rise, the psychological pull of this discovery cannot be overstated. We have, as a species, spent our entire modern era looking for an exit. And in 2015, for one glorious summer, it felt like we had found one. But here is the truth about Kepler-452b. The truth that the press conferences and the breathless headlines and the hopeful simulated images didn't quite capture. The truth that astronomers and astrobiologists and planetary scientists have been carefully, methodically building piece by piece ever since that July announcement almost a decade ago. Kepler-452b is not our salvation. It is not our twin. It is not our escape hatch, or our second chance, or our cosmic backup drive. It may be, instead, one of the most hostile, terrifying, and physically devastating worlds we have ever stumbled upon in our brief exploration of the cosmos. A world that would break the human body within months. A world surrounded by a choking, thickening atmosphere being slowly strangled by a brightening, aging star. A world where every instinct our evolution gave us to survive would be made useless. A world where the very act of standing up could, over time, kill you. And what's more, what may be the most chilling part of this entire story? It might be showing us what Earth looks like in about 1.5 billion years, when our own sun begins its own slow, inexorable descent into old age. Over the next hour and 50 minutes, we are going to explore Kepler-452b not as the glittering Earth 2.0 of your dreams, but as the strange, brutal, scientifically fascinating world that it actually is. We are going to walk through the physics of its gravity, the violence of its volcanism, the horror of its slowly boiling oceans, the terrifying silence of its skies, and the haunting possibility that whatever lived there before us has long since packed up and left. We are going on a journey not toward hope but toward understanding, and understanding, as painful as it sometimes is always worth the trip. So settle in. Let the darkness around you become a little more comfortable. Let your breathing slow. And let me take you, gently and thoroughly, to a world 1,400 light-years away, where our greatest dreams about the cosmos run headlong into the cold, unforgiving mathematics of reality. Before we dive into the physics and the science and the details, I want to ask you something. Right now in this moment, before you know everything you're about to learn, what do you feel when you hear the phrase Earth 2.0? Is it excitement, hope, relief, or is there already a quiet, instinctive part of you that suspects it's too good to be true? Tell me in the comments below. I genuinely want to know what your gut tells you before we begin. Now, let's start with perhaps the most fundamental problem with Kepler-452b. The problem that exists before we even consider the gravity or the volcanoes or the atmosphere or the dying star above it. The problem that would make every other challenge on this list completely irrelevant. The distance, 1,400 light-years. Say it slowly. Roll it around in your mind. 1,400 light-years. This is not a number that human intuition was built to process. We are creatures of savannas and coastlines and mountain valleys, a species that once thought a journey of 50 miles was an epic undertaking. We are simply not wired, at any deep cognitive level, to truly comprehend what 1,400 light-years means. So let me try to help. Light, the fastest thing in the known universe, travels at approximately 299,792 kilometers per second. That's nearly 300,000 kilometers in the time it takes you to blink. In one single second, a beam of light can travel around the entire circumference of the Earth more than 7 times. And even moving at that incomprehensible speed, a photon of light leaving Earth this very moment would not arrive at Kepler-452b for 1,400 years. 1,400 years ago, on Earth, it was approximately the year 625 by the common calendar. The Prophet Muhammad had not yet received the revelation that would give rise to one of the world's major religions. The Viking Age hadn't begun. The Norman conquest of England was still over 4 centuries in the future. The Renaissance was still 900 years away. The Americas were unknown to European civilization. The printing press, the steam engine, the internal combustion engine, the airplane, the computer, the internet, and the entirety of modern science were all waiting to be born. That is how far away Kepler-452b is, measured in the currency of human history. Now, let's talk about actually getting there. The fastest human-made object ever launched from Earth is the Parker Solar Probe, which at its closest approach to the Sun reached speeds of approximately 692,000 kilometers per hour. That is extraordinarily fast by any human standard. It is roughly 0.064% of the speed of light. At that speed, to reach Kepler-452b, the journey would take approximately 2.2 million years. 2.2 million years ago, the dominant species on Earth was Homo habilis. Our immediate ancestors were just beginning to shape simple stone tools. Anatomically modern humans, Homo sapiens, wouldn't appear for another 2 million years. Even if we built an impossibly advanced spacecraft capable of traveling at 1% of the speed of light, far beyond anything we can currently imagine engineering, the trip would take 140,000 years. That is longer than modern Homo sapiens has existed as a species on this planet. At 10% of the speed of light, which is a speed that physicists have seriously explored as a theoretical goal for interstellar travel, still enormously beyond any current technology, the journey would take 14,000 years. Even at the absolute, physically theoretical ceiling, traveling at the speed of light itself, which Einstein's special theory of relativity tells us is impossible for any object with mass, you would arrive at Kepler-452b 1,400 years after you left. And here is where the psychological horror of this distance truly sets in. Imagine that tomorrow, through some technological miracle, humanity builds a spacecraft capable of traveling at the speed of light. You board it. You say goodbye to everyone you love, to your family, your friends, your world. And then you leave. And as you travel, because of the strange effects of special relativity, time passes differently for you than it does for the people you left behind. You might age only slightly during the journey, depending on the specifics of the physics involved. But back on Earth, 1,400 years pass. By the time you arrive at Kepler-452b, every human being who watched your launch has been dead for more than a millennium. The children of those who knew you have had children, who have had children, who have had children for over 40 generations. The world you left has changed beyond all recognition. Multiple civilizations may have risen and fallen. Languages have changed. Nations have dissolved and reformed. The technological and cultural landscape of Earth would be as alien to you as Earth itself might be to someone from medieval Europe transported forward in time to today. Everything and everyone you ever loved is gone. Long gone. The only thread connecting you to Earth is a radio signal. And even that signal, traveling at light speed itself, takes 1,400 years to arrive at Kepler-452b, and another 1,400 years for any response to return. If you sent a message the moment you arrived, asking simply what is happening on Earth right now, you would have to wait 2,800 years for the answer. 2,800 years. That is longer than the entire span of recorded human history from the height of ancient Greece to the present day. That is the lag on your cosmic internet connection. This means that from the moment of departure, you are truly, completely, and irreversibly alone. Not alone in the sense that most of us mean when we say we feel lonely. Not alone in the way of a long-distance relationship or an isolated cabin in the mountains. You are alone in a way that no human being has ever been alone since the first of our kind looked up at these same stars with wonder and confusion. And now consider this. If we ever sent a colony ship to Kepler-452b, whether crewed by human beings through multiple generations, or by human beings in some form of suspended animation or cryosleep, those colonists would know with complete certainty that they are never returning. Earth is not a place they can call home anymore. It is a distant story, a myth, a world described in old digital records and inherited memories. Their children, if they survive long enough to have them on the journey, will have been born in the void between stars, with no lived experience of what a planet even feels like underfoot. And then, if they survive the journey, they arrive. They step out onto the surface of Kepler-452b, and the planet begins trying to kill them immediately. But we'll get to that. For now, I want to sit with the distance for just one more moment, because I think it deserves it. 1,400 light-years represents not just a physical barrier, but a psychological and philosophical one. It raises a question that no government, no billionaire, no space agency, no interstellar dreamers have ever fully answered. If we can never come back, if no one we send can ever return, if the communication delay renders any kind of Earth-based support meaningless, then what exactly is the goal? Is it survival, legacy, curiosity? The desire to leave something of humanity in the cosmos, just in case Earth itself doesn't make it. These are not idle philosophical questions. They are the questions that any serious plan to send humans to another star system must eventually confront and answer honestly. And as of right now, in the early decades of the 21st century, we don't have those answers. We barely have the technology to imagine the question clearly. Here's the question I want to leave you with for this section. If you were told that you could board a ship to Kepler-452b, that the journey would take many generations, and that you would never, under any circumstances, be able to return to Earth or communicate with it in real time, would you go? And if so, what would be the reason strong enough to make you leave everything behind forever? And if not, what is the one thing that would keep you here? Leave your answer in the comments. I want to read every single one. So, we have established that Kepler-452b is impossibly far. That reaching it is, by current physics and technology, essentially a fantasy requiring a revolution in human capability that we cannot yet see on the horizon. But let's continue the thought experiment. Let's say, somehow, impossibly, you've made it. Your ship has crossed the 1,400 light-year void. You've slowed down. You've entered orbit around this planet, and now you're looking down at it from above. What do you see? And more importantly, what are you about to descend into? From orbit, the view might be stunning in its own way, but not in the way the artists who painted the bright, vivid concept images of Kepler-452b might have led you to believe. The first thing you would likely notice, long before you could see any surface features, is the clouds. Not the scattered white puffs that drift across Earth's blue atmosphere on a clear afternoon, not the rolling nimbus formations of a coming storm. We're talking about something altogether different, something heavier, denser, more oppressive. An almost unbroken, planet-wide ceiling of thick, gray-white clouds stretching from horizon to horizon with no obvious breaks, no gaps, no windows through which any light from the surface could escape into space, or through which any starlight from above could reach the ground below. Kepler-452b, by the current best estimates of planetary scientists, would have an extraordinarily thick atmosphere. This isn't a guess or a fantasy. It follows directly from the planet's size and mass. A world that is roughly 1.63 times the radius of Earth, and approximately 5 times its mass, would generate enormous gravitational pressure on whatever atmosphere formed around it. And with that gravitational pressure comes the capacity to hold on to atmospheric gases far more effectively than Earth does. On Earth, our atmosphere extends roughly 100 kilometers above the surface at any meaningful density. Gravity pulls it down and keeps it contained, but not overwhelmingly so. Light gases like hydrogen escape the atmosphere over geological time. Heavier gases like nitrogen, oxygen, and carbon dioxide are held more firmly. On Kepler-452b, with roughly double Earth's surface gravity, the atmosphere would be compressed more tightly and held more firmly against the surface. The total column pressure, the weight of all the air sitting above any given square meter of ground, would likely be significantly higher than on Earth. Some models of super-Earths in this mass range suggest surface pressures potentially several times that of Earth's 1 bar of atmospheric pressure at sea level. Now, already, before we've even talked about what that atmosphere is made of, consider what that pressure means physically. If you've ever descended to the bottom of a deep swimming pool and felt the pressure building in your ears, or if you've dived to any significant depth in the ocean, you know what increased pressure feels like. It squeezes. It pushes back against your body from all directions. You have to work harder to breathe. On a planet with 3 or 4 times Earth's atmospheric pressure, even before accounting for any toxic components, breathing itself becomes a physical challenge. Your diaphragm, the muscle that drives the mechanical work of breathing, would be working against higher external pressure with every single breath. Every inhale would require more effort. Every exhale would push against a heavier column of air. And the composition of that atmosphere almost certainly wouldn't be anything like the oxygen-nitrogen mixture we breathe here on Earth. We'll talk about the specifics of the atmospheric chemistry later in our journey tonight. But for now, suffice it to say that the air of Kepler-452b would almost certainly be unbreathable without mechanical assistance. You would need to bring your own oxygen, your own scrubbers, your own life support from the very first moment you cracked the hatch on your landing craft. But back to those clouds. The thick, dense cloud cover predicted for Kepler-452b has interesting implications for the surface environment. On Earth, cloudy days are cooler days. Cloud cover reflects sunlight back into space, reducing the energy that reaches the ground. But cloud cover also traps heat that's already near the surface, functioning like an insulating blanket. The net effect of any particular cloud system depends on the altitude and thickness of the clouds, among other factors. On a world like Kepler-452b, with this massive planet-wide cloud system, the most immediate effect on surface life would be light, or rather, the lack of it. Even if the star Kepler is slightly brighter than our Sun, which it is by about 20%, an almost unbroken global cloud deck would filter and scatter and absorb the majority of that incoming light long before it reached the surface. The planet's surface, rather than being bathed in warm, golden, life-giving starlight, would exist in a condition more like a permanent overcast day on Earth. Imagine living your entire life under a sky that looks like the sky immediately before a heavy thunderstorm. A sky that is never fully dark, but is never truly bright either. A sky that presses down with a gray heaviness, diffusing light in every direction so that there are no shadows, no patches of direct warmth, no breaks in the opaque ceiling above. The light would be dim and directionless, what photographers sometimes call flat light, the kind of light that drains color and contrast and depth from the world around you. This matters biologically in ways we often underestimate. Human beings have evolved with a 24-hour day-night cycle tied to the brilliance of direct sunlight. Our circadian rhythms, our hormone cycles, our vitamin D production, our mood regulation, our sleep quality, all of these are deeply bound to the presence of true, direct solar radiation. Not filtered, not diffused, but direct sunlight. In countries where cloud cover is persistent through the winter months, like in Scandinavia or parts of the Pacific Northwest, seasonal affective disorder, a form of depression driven partly by light deprivation, is a documented and significant public health concern. A permanent, planet-wide, never-ending cloud deck would push that effect to an extreme from which no seasonal change would ever offer relief. Beyond the light and the pressure and the thickness, there's the question of what the clouds themselves are made of and what they mean for conditions at the surface. Clouds are not always water vapor. On Venus, for instance, the thick, permanent cloud deck that shrouds the planet from space is composed largely of sulfuric acid droplets. Sulfuric acid clouds don't rain water. They rain acid. We don't know the exact composition of Kepler-452b's atmosphere or cloud system. But given the geological activity expected on such a massive rocky world, and given the possible runaway greenhouse dynamics unfolding on the planet, A significant component of sulfur dioxide and other volcanic outgassing products is plausible. This would make even the clouds of this planet, not just the air beneath them, potentially hazardous in ways that go far beyond simple weather. Then there's the temperature below those clouds. The surface temperature of Kepler-452b is one of the most uncertain but critical factors in evaluating its habitability. The equilibrium temperature, what the surface temperature would be without any atmospheric warming effect at all, is estimated at around -8 degrees Celsius. That's cold. But of course, no atmosphere means no greenhouse effect, and that equilibrium temperature is just the raw calculation from the star's energy output and the planet's distance. With a thick atmosphere, even a moderately effective greenhouse warming would push surface temperatures substantially higher, and with the dynamics we'll discuss later, they may have risen substantially higher than that. So the ground-level picture I want you to hold in your mind as a starting point is this. You step out of your lander onto the surface of Kepler-452b. The gravity immediately tells your body, very firmly and very clearly, that something is wrong. The sky above you is a featureless gray-white, as if the entire dome of the heavens has been replaced with a vast diffusion panel. The light is dim, flat, and directionless. The air, even through your suit, pushes against you. The humidity is stifling. The temperature is uncomfortably warm. And somewhere below your feet, in the deep rock of this world, the planet is alive with heat and movement in a way that Earth only shows us in its most geologically active regions. This is your first impression of Kepler-452b, and it is about to get much worse. I'm curious about something. When you imagine stepping off a spaceship onto an alien world for the very first time, what do you picture? Is it a dramatic, cinematic moment of awe and wonder, the way science fiction has taught us to picture it? Or does the thought, if you're honest with yourself, come with some element of fear or dread? Comment below with your honest gut reaction to the idea of standing on an alien planet for the very first time. No wrong answers here. That oppressive feeling you'd get just from the sky, the pressure, the dim gray light, that's just the backdrop. Now let's talk about what your body is doing while you're standing there taking it all in. Because Kepler-452b's most immediate, most relentless, and most unavoidable threat is something you cannot see, cannot smell, cannot taste, and cannot reason your way out of. It is the gravity, and it is working on your body the moment you arrive. And it will not stop. Not for a single second of every single day you spend on this world. Let's start with the basics, because the concept of surface gravity is one that most of us have an abstract understanding of, but very few of us have ever had reason to think about deeply. Surface gravity is the acceleration that a planet's mass exerts on objects on its surface. On Earth, this value is approximately 9.8 meters per second squared, a number so embedded in our physics textbooks that it has its own symbol, lowercase g. This is the force that keeps your feet on the ground, the force that makes things fall, the force that your body's entire architecture, from your skeletal structure to your cardiovascular system to the shape of your cells, has spent hundreds of millions of years of evolution learning to function within. On Kepler-452b, with a mass approximately 5 times that of Earth and a radius approximately 1.63 times that of Earth, the surface gravity is estimated to be roughly 2 times Earth's surface gravity. 2g, that's it. 2. Just 2 times what you're experiencing right now as you sit or lie wherever you are. That seems manageable, doesn't it? 2 times gravity. It doesn't sound that dramatic, not when we're talking about a planet that might be humanity's alternate home. Surely we'd adapt. Surely technology would compensate. Surely human ingenuity would find a way. Let me show you why 2G is not manageable, not for a human body, not for any meaningful period of time. Stand up right now if you can. Now imagine someone placing a duplicate of yourself directly on your shoulders. Another full, complete human being of your exact weight, sitting on you, riding on your body permanently. Forever. That is what 2G feels like. That is the immediate, constant, inescapable experience of existing on a two-gravity world. Every step you take requires twice the muscular effort. Every time you lift your arm to reach for something, you are fighting against twice the pull of a planet. Carrying a 5-kilogram bag of groceries feels like carrying 10 kilograms. Climbing a flight of stairs feels like climbing 2 flights. Standing in line for any length of time causes your legs to ache and your lower back to tighten in protest. Even lying down offers no true relief, because the pressure of twice the gravity still compresses every joint, every disc, every vessel in your body against the surface beneath you. But this is just the immediate, obvious effect. The real horror of 2G is what it does to the human body over time, in ways that are hidden, systemic, and ultimately lethal. Let's start with the heart. Your heart is a pump. Its job is to move blood around your body from your lungs, where it picks up oxygen, to every cell, organ, and tissue in your body, and then back again. To do this, it has to push blood upward against the pull of gravity, all the way to your brain, which sits roughly a meter above your heart when you're standing. On Earth, your heart handles this with remarkable efficiency. It generates enough pressure to push blood upward against 1G of gravity, maintaining adequate circulation to the brain even when you stand, run, jump, or exercise vigorously. The pressure it generates is what we measure as blood pressure, and a healthy heart manages this for decades without significant structural damage. Now double the gravity. The heart must now generate significantly more pressure to push blood upward against twice the gravitational pull. Your blood is twice as heavy. Your circulatory system, from arteries to capillaries to veins, was not built for this sustained load. The heart muscle must work harder with every single beat, every single day, every single hour, with no rest and no relief. Over time, this causes what cardiologists call pressure-induced hypertrophy. The heart muscle thickens and enlarges in an attempt to compensate for the increased workload. The artery walls stiffen and thicken under chronic high-pressure stress. The risk of arterial damage, aneurysm, and catastrophic cardiovascular failure increases dramatically. Without significant medical intervention targeting the cardiovascular system specifically, the heart of a person living under 2G gravity would begin to fail within years, possibly within just 1 or 2. Then there's what happens below the heart. In a 1G environment, your body already struggles with fluid distribution in the lower limbs. Sit at a desk all day and your ankles swell. Stand for hours without moving and your legs ache with pooled blood. Now multiply the gravitational force pulling fluid downward. Blood, lymphatic fluid, and intracellular fluids would pool aggressively in the lower extremities. Legs would swell continuously and progressively. Veins would distend and distort. Deep vein thrombosis, the formation of dangerous blood clots in the deep veins of the legs, would become a chronic, life-threatening risk rather than an occasional inconvenience associated with long flights and sedentary behavior. The spine would be under siege as well. Your intervertebral discs, the gel-filled cushions between each vertebra that absorb shock and maintain the spacing that prevents nerve compression, are already under constant compressive load in 1G. They lose height gradually over the course of a normal day, which is why you are measurably shorter at night than you are in the morning, a phenomenon called diurnal height variation. In 2G, this compression is doubled. Discs degenerate faster. The gradual narrowing of the spaces between vertebrae brings bone surfaces closer to nerve pathways. Nerves get pinched. Chronic, severe back pain would be a constant companion, not an occasional complaint, and the progression towards serious nerve damage would be measured in years rather than decades. Your lungs, too, would struggle under doubled gravity. The diaphragm, the main muscle of breathing, would be pulling against twice the weight of the chest wall and the abdominal organs below with every breath. Breathing would require more muscular work than it does at sea level on Earth, and significantly more than it requires at altitude, where reduced atmospheric pressure gives the diaphragm a slightly easier mechanical load. For anyone with any pre-existing respiratory condition, the effect would be immediate and severe. For those who appear perfectly healthy by Earth standards, the extra respiratory work would add to the cumulative physiological burden and accelerate fatigue. The brain itself is not spared. Getting adequate blood to the brain becomes harder in high gravity, especially when standing and when changing positions quickly. Orthostatic hypotension, the positional lightheadedness and brief visual dimming that many people occasionally experience when standing up quickly from a seated or lying position, would be far more frequent and far more severe under 2G. Chronic subclinical reduction in cerebral blood flow, meaning a persistent slight underdelivery of oxygenated blood to brain tissue, would impair cognition gradually and insidiously. Reaction times, working memory, executive function, and overall cognitive clarity would all be affected in ways the colonist might not even consciously notice at first. And this says nothing yet of the bone and joint consequences. Your skeleton is not static. It is constantly being broken down and rebuilt by specialized cells, in a process regulated in part by the mechanical stress placed on the bones. Under 2G, bones would be under twice the load they evolved to bear. They would likely respond by increasing their density over time in an attempt to adapt. But this increased density and mass would place further strain on the joints that must carry this heavier skeleton, and the cartilage surfaces of those joints would wear away faster, leading to early onset and rapid progression of osteoarthritis throughout the major weight-bearing joints of the body. Studies on long-duration spaceflight, which subjects the human body to the opposite problem, the zero gravity of orbit, have given us tremendous insight into how profoundly sensitive human physiology is to gravitational environments outside the 1G in which it evolved. In microgravity, the cardiovascular system deconditions. Bones lose density at an alarming rate. Muscles atrophy rapidly. The spine elongates as discs expand without compressive load. The face becomes puffy from fluid redistribution. These effects occur within weeks to months, and some prove difficult or impossible to fully reverse even after return to Earth. In 2G, the effects would be in the opposite direction, but no less severe and no less rapid. The system would be stressed rather than atrophied, but overstressed to the point of accelerated damage and failure. Experiments on animals subjected to elevated gravity conditions, conducted primarily using centrifuges over sustained periods, consistently show impaired health outcomes, reduced lifespan, reproductive difficulties, and systemic organ stress across a wide range of species. The human body, for all its remarkable adaptability, was never engineered to function under twice the gravitational load of the environment in which it spent the last several million years evolving. Without medical technology specifically designed to counteract the cardiovascular strain, the fluid dynamics, and the skeletal compression of living under 2G, the human lifespan on Kepler-452b would likely be dramatically shorter than on Earth. We're talking decades shorter, not years, decades. And remember, this is in addition to all the other hazards we have not yet discussed. Here's a question I want you to think about carefully. What do you think the absolute minimum level of technology would need to be for a human civilization to survive, not just visit, but actually live and thrive under 2G gravity? We're talking infrastructure, medicine, architecture, clothing, food production, transportation, everything. How radically different would the design of every human tool and every human system need to be? Let me know your thoughts in the comments below. So the gravity would be wearing us down from the inside, slowly and relentlessly, from the very first moment we arrived. But what about the ground under our feet? What would the surface of Kepler-452b actually be like to walk on, to build on, to try to make a home on? The answer, unsurprisingly, is deeply unsettling. Because beneath the surface of this massive world, trapped in a core that holds far more heat than Earth's own interior, something is churning, something is pushing, something is looking for a way out, and it has been looking for a very, very long time. Every terrestrial planet in our solar system, and by all planetary science accounts every rocky planet anywhere in the universe, has an interior that is hot. This is not a mystery. Planets form from the violent collision and aggregation of rock and ice and dust over millions of years, and the energy of those collisions is converted into heat during the accretion process. Additionally, radioactive isotopes trapped inside the planet during formation decay over billions of years, generating a steady internal heat source that persists long after the planet's formation is complete. Earth's interior is extraordinarily hot by any human standard. The outer core, primarily composed of liquid iron and nickel, reaches temperatures of around 4,000 degrees Celsius. The inner core is even hotter, nearly 6,000 degrees Celsius, roughly as hot as the surface of the sun. This vast reservoir of internal heat has shaped everything about our planet's surface over its entire geological history. It drives plate tectonics, the slow but ceaseless movement of the enormous slabs of rock that make up Earth's crust. It fuels the volcanoes that have, over geological timescales, built our continents, shaped our ocean basins, and released the gases that formed our atmosphere. Now scale that up. Kepler-452b, with a mass approximately 5 times that of Earth, would have formed from a proportionally larger and more energetic collision process. More mass, more impact energy, more initial heat generated during accretion. Additionally, more radioactive material was captured within the planet's formation zone, providing a larger and longer-lasting internal heat source from radioactive decay. And with a larger planet, the ratio of surface area to total volume decreases significantly, meaning the planet retains its internal heat far more efficiently than a smaller world. A larger body simply cools more slowly, in the same way that a large pot of boiling water stays hot for far longer than a small cup. The result is a planetary interior that is, by all reasonable geological estimates, significantly more energetic than Earth's own interior, even accounting for Kepler-452b's greater age. There is, however, an additional and deeply counterintuitive complication that planetary scientists have been working through in recent years. Super-Earths, planets in the mass range of roughly 1 to 10 times Earth's mass, may actually experience a form of tectonics very different from Earth's familiar plate tectonic system. On Earth, the crust is divided into about 15 major tectonic plates, and these plates move relative to each other, driven by convection currents in the mantle below. This produces earthquakes at plate boundaries, volcanoes at subduction zones where one plate dives below another, and the slow, beautiful waltz of continental drift over hundreds of millions of years. This process also serves a critical function in regulating atmospheric chemistry by recycling carbon and other elements between the surface and the interior. On super-Earths in Kepler-452b's mass range, the situation may be dramatically different. The higher gravity means higher pressures on the rocky mantle, and higher pressures mean that the rock behaves differently at depth. The minerals that make up the mantle transform into different high-pressure crystal phases at depths much shallower than on Earth. Some planetary models suggest that super-Earths may experience what's called stagnant lid tectonics. Instead of a broken mosaic of moving plates drifting against each other in a dynamic system, the entire crust may effectively be a single, immovable lid, sitting on top of a vigorously convecting mantle below. At first glance, this might sound like it would reduce volcanic activity. If the plates aren't moving, there are no subduction zones to create volcanoes at convergent boundaries. But the reality of stagnant lid tectonics is quite different from this intuition. Without the plate tectonic recycling mechanism, the heat that builds up in the mantle has very limited pathways to escape. It creates enormous mantle plumes, giant columns of superheated rock that rise from the deep interior and punch through the rigid lid above, creating what geologists call hotspot volcanoes. On Earth, the Hawaiian Islands are the most famous example of hotspot volcanism, created as the Pacific Plate slowly moves over a stationary mantle plume. But on a stagnant lid world, with far more internal heat and no plate movement to distribute that heat laterally, these hotspot eruptions are likely to be far larger, far more frequent, and far more sustained than anything in Earth's ordinary geological experience. Think of the largest volcanic events in Earth's history. The Siberian traps, which erupted approximately 252 million years ago and are strongly implicated as the primary driver of the Permian-Triassic mass extinction, the greatest extinction event in Earth's entire history, released such enormous quantities of lava ash and sulfur dioxide that they darkened the skies and altered the climate of the entire planet for hundreds of thousands of years. The Deccan traps, which erupted around 66 million years ago in what is now India, contributed significantly to the conditions surrounding the end of the dinosaur age. These events were civilization-ending in scale, even though no complex civilization existed to be ended. On Kepler-452b, events of this magnitude may not be geological anomalies occurring once every 100 million years or so. They may be the ordinary background rhythm of the planet's geological life. The implications for surface habitability are profound. Building anything on the surface of Kepler-452b would require solving engineering challenges of a scale that makes even our most ambitious earthly construction projects look modest. Foundations would need to withstand not just normal geological settling and occasional seismic activity, but a surface that could experience Siberian trap-scale eruptions as relatively routine geological events. Any settlement would need to be able to survive ground movements and lava flows of a type and frequency that no human infrastructure has ever been designed to withstand. But it's not just the physical shaking and erupting that presents the problem. Active volcanoes release gases, lots of gases. The primary volcanic gases are water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, hydrogen fluoride, and carbon monoxide, among others. On Earth, these emissions are diluted into a large, chemically complex atmosphere and distributed globally. Our atmosphere has mechanisms, like the carbon silicate cycle and the hydrological cycle, for processing and sequestering some of these gases over geological time, keeping their concentrations at levels that life can tolerate. On a hypervolcanic world like Kepler-452b, the outgassing rate would be far higher than on Earth. Sulfur dioxide, a toxic gas that in high concentrations causes severe respiratory damage, chemical burns to airways, and long-term lung scarring, is also the primary ingredient in acid rain. It combines with water vapor in the atmosphere to form sulfuric acid, which then falls as rain that corrodes metals, dissolves carbonate rocks, and renders any open water source chemically hostile to life. Even if you were wearing protective suits against the gravity and the pressure and the temperature, the atmosphere outside your habitat would be laden with volcanic gases that slowly degrade unshielded equipment, corrode every exposed surface, and make the air outside lethally toxic without constant filtration. There's an additional geological dynamic worth understanding here. On Earth, one of the primary reasons that volcanic outgassing hasn't poisoned our atmosphere beyond recognition over geological time is that plate tectonics actively recycles carbon dioxide. When oceanic plates dive into the mantle at subduction zones, they carry carbonate sediments, which are essentially rocks made of carbon extracted from the atmosphere by biological and chemical weathering processes, back into the interior, where they are eventually re-released as CO2 through volcanic activity. This is the long-term carbon cycle, the carbon silicate cycle, and it's one of Earth's great climate stabilization mechanisms. On a stagnant lid world, this efficient recycling mechanism doesn't operate in the same way. Carbon dioxide released by volcanism tends to accumulate in the atmosphere rather than being efficiently returned to the mantle. And accumulating CO2, as we know from our own planet's very immediate experience with fossil fuel emissions, is a powerful greenhouse gas with powerful warming effects. So we have a world with more volcanic activity than Earth, potentially less efficient mechanisms for removing the CO2 released by that activity, and a hotter star above that is already pushing the planet toward the inner edge of the habitable zone. These are not independent problems. They are interconnected, self-reinforcing, compounding problems. And standing on the surface of this world, even if you had somehow survived the gravity and the pressure and the dim gray sky, you would feel the ground trembling beneath your boots with a regularity that no human nervous system was ever meant to tolerate as ordinary background experience. Here's what I want to know from you. We have volcanically active regions on Earth, places like Iceland and Japan and parts of the Pacific Northwest, where people have chosen to live for centuries despite the geological risks. Do you think the psychology of human settlement and the ancient, irresistible drive to colonize could overcome the fear of living on a hypervolcanic world? If the alternative was staying on a dying Earth, would people actually choose to live there, knowing the ground beneath them was never truly still? Tell me below. So the ground shakes, the sky is gray, the air is toxic, the gravity is crushing, and somewhere in the dim light filtering through an oppressive cloud deck, you are beginning to wonder if this was a terrible idea. And then you decide, maybe we should leave. Maybe this isn't the planet for us. Let's get back in the ship and find somewhere else. And this is where Kepler-452b delivers its most permanent and irreversible consequence. You can't leave. Escape velocity. The term sounds simple enough, and the concept, once explained, is almost elegantly straightforward. It is the minimum speed that any object must reach in order to permanently escape the gravitational pull of a planet, without any further propulsion after that initial burst of speed. If you can get a rocket to that velocity, it will continue to move away from the planet forever, never to return, no matter how much gravity pulls at it. If you fall short of escape velocity, no matter how high you go, gravity will eventually win and pull you back. On Earth, escape velocity is approximately 11.2 kilometers per second, roughly 40,000 kilometers per hour. This is already an astonishing speed by any human reference. The fastest bullet ever measured travels at about 2 kilometers per second. The speed of sound through air is about 1/3 of a kilometer per second. 11.2 kilometers per second is so fast that, if you maintain that speed horizontally, you would circumnavigate the globe in approximately 1 hour. Getting to that speed is enormously energy-intensive, which is why rocket fuel is measured in hundreds of thousands of kilograms just to get a relatively modest payload into low Earth orbit. Space travel from Earth is expensive, difficult, and technologically demanding, even with 6 decades of experience and engineering iteration behind us. Every major orbital mission requires a vehicle the vast majority of whose mass is propellant, not payload. The passengers, the cargo, the equipment, they represent a tiny fraction of the total launch mass. The rocket's job is almost entirely to carry enough fuel to accelerate itself, and then to burn that fuel efficiently enough to reach orbital or escape velocity before it runs out. Now let's consider what happens on Kepler-452b. With a mass approximately 5 times that of Earth and a radius approximately 1.63 times that of Earth, the surface gravity, as we've already discussed, is roughly double. And escape velocity scales directly with a planet's gravitational field. The precise calculation gives us an escape velocity for Kepler-452b of somewhere in the range of 17 to 20 kilometers per second. Let's call it approximately 19 kilometers per second for a reasonable working estimate. That's nearly 70% higher than Earth's escape velocity. 70% higher. This might sound like a modest percentage difference, but rocket engineering does not scale linearly. It obeys a deeply, mathematically humbling relationship called the Tsiolkovsky rocket equation, sometimes simply called the tyranny of the rocket equation by engineers and mission designers. And it is one of the most brutally honest pieces of mathematics in all of applied science. The rocket equation states, in essence, that the amount of propellant needed to reach a given velocity increases exponentially as the required velocity increases. Not linearly, exponentially. This means that each additional kilometer per second of velocity you need doesn't require just a proportionally larger amount of fuel. It requires substantially, disproportionately more fuel, because you also have to carry the fuel needed to accelerate the fuel itself, and the fuel needed to accelerate that fuel, spiraling outward in a recursive calculation that becomes increasingly brutal with every increment of required velocity. To put this in concrete terms, consider the Saturn V rocket, the most powerful rocket ever successfully flown, which launched the Apollo missions to the Moon. At liftoff, the Saturn V weighed approximately 2,900,000 kilograms. Of that enormous total mass, approximately 2,100,000 kilograms was propellant. The remaining 800,000 kilograms was the rocket structure, engines, and all payload combined. The ratio of propellant to total mass was about 72%. Now, to launch the same payload from Kepler-452b, where escape velocity is roughly 70% higher, the required propellant mass would scale so dramatically that a rocket of Saturn V design and proportions simply couldn't do it. Not without a vehicle that is many, many times larger. Some physicists who have examined this problem in detail have concluded that the fuel requirements to launch even a modestly sized payload from the surface of Kepler-452b into orbit, and then escape velocity exceed what any reasonably engineered chemical rocket could achieve, regardless of its size. The rocket becomes its own paradox. The more fuel you add to reach escape velocity, the heavier the rocket becomes, which requires even more fuel to lift off in doubled gravity, which makes the rocket heavier still, which requires more fuel. You spiral toward an impossible number very quickly. Nuclear propulsion, often discussed in advanced aerospace circles as a future alternative to chemical rockets, could theoretically provide the thrust-to-weight ratio needed to escape from a 2G planet. Ion drives and nuclear pulse propulsion concepts have been studied seriously. But even here, the engineering challenges on a world of this gravity would be extraordinary. You would be building rocket engines in double gravity. Your construction equipment would be twice as heavy. Your fuel tanks must withstand twice the structural loads during fueling and pre-launch. Your launch infrastructure must be built to handle twice the forces of any equivalent facility ever conceived on Earth. And this is all hypothetical, of course, because the most crushing irony of the escape velocity problem is this. Even if you arrived at Kepler-452b, with complete technical knowledge of how to build a nuclear-capable launch vehicle capable of escaping its gravity. The raw materials and manufacturing capability needed to actually build such a rocket from scratch on the planet's surface would require a full industrial civilization already established there, not a colony of a few hundred or a few thousand people surviving in habitat modules. A civilization, a manufacturing base, a supply chain, an engineering workforce, infrastructure of a scale that takes generations to build in an environment that is actively trying to kill everyone building it. You cannot arrive with a prefabricated escape rocket. The mass of such a rocket, plus its fuel, would be so enormous that launching it from Earth and delivering it intact to a world 1,400 light-years away would be a task orders of magnitude beyond anything humanity has ever attempted, planned, or is anywhere near capable of accomplishing. Which means that the first humans to land on Kepler-452b would not be there with the option of leaving. They would be there permanently, not by choice, by physics. This point deserves a moment of quiet contemplation, because it is perhaps the most definitively civilizational statement we can make about Kepler-452b. Every human migration in our species' long history has had, at minimum, the theoretical possibility of return. The people who walked across the Bering Land Bridge from Asia into the Americas 15 to 20,000 years ago could, in principle, have walked back, and some may have. The Polynesians who sailed across the vast Pacific to settle Hawaii could sail home, and records suggest many did make return voyages. Even the most remote, most challenging human settlements in history, from Antarctica to the Himalayas to the most isolated islands on Earth, have maintained some connection to the wider world, some possibility of retreat or rescue. Landing on Kepler-452b would be the first migration in human history with literally no path back. Not a dangerous path, not an uncertain path, no path. The phrase "no return" is one we use casually in ordinary life. No return policies, no return tickets. But we've never genuinely reckoned with what it means at the scale of an entire world. To step onto the surface of Kepler-452b is to close a door behind you that has no handle on the other side. For the rest of your life, however long or short that life turns out to be under double gravity, volcanic clouds, and toxic air, you will never see Earth again. You will never feel Earth's gentler gravity lift you with each step. You will never breathe air that was not bottled, recycled, or manufactured. You will never watch a sunset that isn't filtered through a ceiling of permanent cloud. And your children, if you have them, will grow up knowing nothing else. Here's the question I want you to sit with and share below. The greatest explorers in human history ventured into unknown territory with no guarantee of return. Magellan's crew circumnavigated the globe not knowing if they'd survive. Shackleton and his crew endured impossible conditions in Antarctica. Do you think the no-return constraint of a mission to Kepler-452b would ultimately deter humanity from trying? Or do you think there would always be volunteers willing to make the final, one-way journey? What would make someone say yes to that? So far, every problem we've discussed has been immediate. Gravity you feel the moment you land. Clouds you see the moment you look up. Volcanic instability you sense through your boots within hours. The escape velocity trap you understand the moment you try to think about going home. But the next layer of this story is different. It's slow. It's patient. And it has been building for billions of years, long before the first human ever looked at the night sky and wondered what lay beyond. It begins not with the planet but with the star above it. Stars are not permanent. This is something we know intellectually, but it is surprisingly difficult to feel in our bones, in the way that we feel other facts about the universe. We look up at the night sky, and the stars seem fixed, eternal, unchanging. the same patterns that guided the sailors and the shepherds and the astronomers of 10,000 years ago. They were there long before us, and our deep, instinctive sense is that they will be there long after us. But stars age. Stars are born, they mature, they grow old, and eventually they die. And the changes they go through on the long path to dying matter enormously to any planet that happens to be orbiting them. Our own sun is a middle-aged star. Born approximately 4.6 billion years ago from a collapsing cloud of gas and dust in the Milky Way, it is about halfway through its main sequence life, the long, stable phase during which it fuses hydrogen into helium in its core. This process will continue for roughly another 5 billion years, after which the sun will begin to exhaust its core hydrogen fuel, and its behavior will change dramatically, expanding outward into a red giant and ultimately shedding its outer layers in a beautiful but deadly stellar transformation that will consume the inner planets. But here's the key insight, and it's one that most people don't fully appreciate. Even during the main sequence, even during the long, stable phase of hydrogen burning, stars do not remain completely unchanged. They slowly, gradually brighten. As hydrogen fuses into helium, the helium accumulates in the core. The core gradually becomes denser and hotter in order to maintain the pressure needed to balance the gravitational force pulling inward. And a hotter, denser core means more energy is produced per unit time, more luminosity radiated outward. Over Earth's 4.5 billion year history, our sun has brightened by approximately 30 to 40%. The sun of 4 billion years ago was significantly dimmer than the sun we see today. This is actually one of the fascinating puzzles in planetary science, called the faint young sun paradox, because geological evidence shows that Earth had liquid water on its surface, even when the sun was significantly dimmer than today. The planet stayed warm enough for liquid water through the combined effects of a warmer geological interior, higher concentrations of greenhouse gases in the early atmosphere, and other factors that planetary scientists continue to refine. But the critical point is this: our sun is brightening, slowly, almost imperceptibly on human timescales, but relentlessly over geological time. Now let's turn our attention to Kepler-452. Kepler, the star that Kepler-452b orbits, is an extraordinarily close analog to our sun in stellar type. It's classified as G2 main sequence, the same classification as the sun. It has approximately 1.04 solar masses, slightly more massive. Its surface temperature is right in the same ballpark as the sun's. In terms of stellar type, age class, and general behavior, Kepler and our sun are as close to siblings as the galaxy has to offer. But here is the critical difference between them. Kepler is approximately 6 billion years old. Our sun is approximately 4.6 billion years old. That is a difference of roughly 1.4 billion years. 1.4 billion years of additional stellar aging. 1.4 billion additional years of that slow, inexorable brightening. In stellar terms, this means that Kepler has been on the main sequence for 1.4 billion years longer than the sun. During that time, following the same brightening process that our sun undergoes, Kepler has brightened significantly compared to its own younger past. Current measurements place Kepler at approximately 1.2 times the luminosity of our sun, 20% brighter, emitting roughly 10% more energy in the specific solar flux values that drive planetary surface heating. Now, imagine taking Earth today exactly as it is and placing it in orbit around a sun that is 20% brighter. What happens? This is not a hypothetical question. This is essentially the situation that Kepler-452b faces right now in its orbit around its aging star. And the answer, according to the models, is deeply sobering. Earth sits comfortably within our sun's habitable zone today, with significant margin from the inner boundary. The inner edge of the conservative habitable zone, the point at which the greenhouse effect would become self-reinforcing and irreversible for an Earth-like planet, is roughly 95% of Earth's current orbital distance. We have about 5% of orbital distance between us and that boundary. For now. Kepler-452b, at 1.046 astronomical units from a star 20% more luminous than the Sun, receives substantially more energy per unit area than Earth does from our Sun. Detailed calculations place the planet at or very near the inner edge of the habitable zone, or possibly slightly inside it, depending on which atmospheric models are used and which precise definition of the habitable zone boundary is applied. This means that Kepler-452b may be receiving just enough additional energy from its aging, brighter star to trigger a process that we understand from Venus, from the early history of Mars, and from our own planet's atmospheric science in increasing detail. A process called the runaway greenhouse effect. But before we get into that particular horror, let's pause on the age difference itself for just one more moment. 1.4 billion years. This is an almost incomprehensibly long period of time. The entire evolutionary history from the first fish with primitive limbs crawling tentatively out of shallow Devonian seas to the first modern human standing upright on the African savanna took less than 400 million years. The age difference between Kepler and our Sun is more than 3 times longer than that entire evolutionary journey from Finns to Homo sapiens. What this means is that if Kepler-452b ever had, or still has, life of any kind, that life has had a 1.4 billion year head start over anything on Earth. Life on Earth has been complex and multicellular for roughly 540 million years, since the extraordinary burst of biological innovation called the Cambrian explosion. If life on Kepler-452b started at a similar point in its planet's history and followed a vaguely similar trajectory of increasing complexity, that life has been complex and multicellular for approaching 2 billion years. 2 billion years of evolutionary advantage. And yet, when we look at Kepler-452b today, what do we find? We'll get to that in our fourth act. But first, the star's age is not just interesting from a life history perspective. It is directly responsible for what may currently be happening on the planet's surface. Because that extra 20% luminosity is the engine driving the next catastrophe in our story. Here is a question for you to ponder and share in the comments. Our own Sun will brighten over the next billion to 2 billion years, eventually pushing Earth out of the habitable zone, just as Kepler-452 appears to be doing to its planet right now. If you knew that Earth had approximately 1 billion years of habitability left, do you think humanity has an obligation to begin planning for that reality now? Or is that simply too distant to matter to any living civilization? I'm genuinely curious what you think about this. That extra starlight falling on Kepler-452b isn't simply a matter of temperature. It isn't that the planet is running a degree or two warmer than it used to. The extra energy pouring from Kepler-452 is triggering a cascade of interconnected atmospheric and geological processes that, taken together, are systematically and relentlessly dismantling whatever habitability Kepler-452b may once have possessed. This cascade has a name. We call it the runaway greenhouse effect. And it is, in every measurable sense, potentially the planet's death sentence. Let's begin with the version you already know. The greenhouse effect, at its most basic, is simply the process by which certain gases in a planet's atmosphere absorb and re-emit infrared radiation, trapping heat near the planetary surface rather than allowing it to radiate back into space. This is not, in itself, a harmful or unusual thing. Without any greenhouse effect at all, Earth's average surface temperature would be around -18 degrees Celsius, which is effectively uninhabitable for most of the life we know. The roughly 33 degrees Celsius of warming that Earth's natural greenhouse effect provides, primarily from water vapor, carbon dioxide, and methane, is what makes liquid water, and therefore life, possible on our planet. The greenhouse effect is not the villain of Earth's story. It is the reason Earth has a story. The key is balance. The greenhouse effect must be strong enough to keep the planet warm, but not so strong that it spirals out of control. When it spirals out of control, the result is called the runaway greenhouse effect. And to understand what a runaway greenhouse looks like on a planetary scale, we need look no further than our own solar system's tragic and instructive case study: Venus. Venus, our nearest planetary neighbor, is often mentioned as Earth's twin because it is almost exactly the same size and mass as Earth. It formed from the same stellar neighborhood, from the same broad disk of material in the early solar system. And there is strong geological evidence, increasingly supported by recent planetary science, that Venus long ago may have had liquid water on its surface for an extended period. It may have been habitable. It may once have been somewhat like Earth, but something changed. Whether it was a gradual accumulation of carbon dioxide from volcanic activity, or a modest increase in solar luminosity as the young sun brightened, or some combination of both factors acting together, at some point Venus crossed what's called the moist greenhouse threshold. Its surface became warm enough that water began to evaporate more aggressively into the atmosphere. Water vapor, remember, is itself a powerful greenhouse gas. More water vapor in the atmosphere trapped more heat near the surface. More heat caused more evaporation of surface water. More evaporation added more water vapor to the atmosphere. The feedback loop, once started, could not be stopped by any natural mechanism. As the atmosphere accumulated more and more water vapor, the upper atmosphere became saturated. Ultraviolet radiation from the sun broke the water molecules apart into their constituent atoms, hydrogen and oxygen, through a process called photodissociation. Hydrogen, being the lightest element, escaped to space, lost forever. The oxygen combined with other atmospheric gases or was absorbed into surface rocks. Over tens to hundreds of millions of years, Venus lost its water entirely. Every ocean, every lake, every drop of rain, gone. And without liquid water, the geological process of carbon sequestration, the weathering of silicate rocks that absorbs CO2 from the atmosphere and locks it into carbonate minerals, shut down completely. Carbon dioxide from volcanic activity accumulated in the atmosphere with nothing to remove it. The greenhouse effect intensified further. Surface temperatures rose to their current catastrophic levels of nearly 465 degrees Celsius, which is hot enough to melt lead and hot enough to soften zinc. Venus today has a surface pressure 92 times that of Earth, a sky permanently hidden behind thick sulfuric acid clouds, and an average surface temperature higher than Mercury, the closest planet to the Sun. By any meaningful definition, Venus is the geological equivalent of hell. And it was not always so. Kepler-452b may be walking the same path. Possibly, it is already partway down that road. The host star's extra 20% luminosity means that the energy reaching Kepler-452b's surface is substantially greater than what Earth receives from our Sun. Scientists who have modeled the planet's atmospheric dynamics have noted that it sits uncomfortably close to, or possibly just inside, the inner edge of the habitable zone, defined as the point at which the moist greenhouse effect begins to become self-sustaining and irreversible. If surface temperatures on Kepler-452b have risen enough to trigger accelerated water evaporation into the upper atmosphere, The same cascade that doomed Venus may now be playing out in a stellar system 1,400 light-years away, in slow and majestic and terrible silence. Here is what that process looks like in practice. The oceans of Kepler-452b, if they still exist in any meaningful form, are absorbing more energy from the star than they can efficiently radiate back to space. The surface water warms. As it warms, it evaporates more readily, sending water vapor into the atmosphere. Water vapor is the most potent greenhouse gas in terms of sheer abundance in a planetary atmosphere, so this addition of atmospheric moisture traps more heat near the surface. The surface warms further. More evaporation occurs. More water vapor enters the atmosphere. More warming follows. The cycle feeds itself. The oceans don't boil all at once, dramatically, in the way that science fiction sometimes depicts for visual effect. The process is slow on human timescales, though fast on geological ones. The waters warm. They shallow. They retreat from coastlines that were once covered by ocean floor. Islands and continents grow as the global sea level drops, not because ice is forming somewhere else, but because the water is leaving the liquid phase entirely rising into the air as vapor rising further into the upper atmosphere. And they're being dissociated by ultraviolet radiation and lost permanently to space. The remaining water concentrates into progressively saltier, progressively warmer, progressively shallower bodies. The chemistry of any remaining seas becomes increasingly hostile to the complex biochemistry that life, as we understand it, requires. The temperature range for stable protein folding, for DNA replication, for cell membrane integrity, all of this narrows and eventually disappears entirely. As the oceans recede, the geological process of CO2 sequestration slows, because that process requires liquid water to weather rocks and carry dissolved carbon compounds toward the ocean floor. With less liquid water, less carbon is removed from the atmosphere. Volcanic activity continues unabated, releasing CO2. The atmosphere thickens with CO2. The greenhouse effect intensifies. The surface heats further. The remaining water evaporates faster. The oceans shrink further. This is the cascade, and once it reaches a certain threshold, it does not reverse on any timescale relevant to life or civilization. What does all of this mean for the surface of Kepler-452b right now, tonight, as you listen to this? It depends on exactly where in this process the planet currently sits. If the runaway greenhouse has not yet begun in earnest, the surface may still have liquid water, albeit in a warmer, muggier, more geologically turbulent form than Earth's current oceans. If the process is in its early stages, the planet may be experiencing conditions roughly analogous to what Earth might experience in several 100 million to 1 billion years, as our own sun continues its slow brightening toward the same threshold. If the process is more advanced, the planet may be in the final stages of ocean loss, its atmosphere thickening with water vapor and carbon dioxide, its surface temperatures already crossing the boundary at which most complex life becomes physiologically impossible. What makes this particularly philosophically striking is this. Kepler-452b may not be showing us what an alien world looks like on some entirely different trajectory. It may be showing us what Earth will look like in approximately 1.5 billion years, when our own sun has brightened enough to push our own planet past the moist greenhouse threshold. Earth's future, visible across the cosmos. Playing out in real time while we watch, with nothing we can do to intervene at this distance, and perhaps not much we could do even at close range. Here's a thought I'd love for you to share in the comments. The idea that Kepler-452b might be a preview of Earth's far future is one of the most philosophically challenging concepts in all of exoplanetary science. Does that knowledge change how you feel about Earth's long-term future? Does it make you feel more urgency about protecting Earth now? Or does the timescale feel too vast to make it emotionally real? I want to know. So the oceans are boiling away. The star is brightening. The greenhouse effect is spiraling upward with no natural mechanism to stop it. And the atmosphere is changing in ways that go far beyond simple temperature increases. Because as the water vapor accumulates and the carbon dioxide builds and the volcanic outgassing continues unabated, the air itself becomes something very different from the oxygen-rich atmosphere that humanity breathes on Earth. Let's talk about what you'd actually be breathing on Kepler-452b. Or rather, what you'd be trying very hard not to breathe. We breathe approximately 20,000 times per day. Each of those breaths pulls a mixture of about 78% nitrogen, 21% oxygen, and 1% of everything else through our lungs, delivering oxygen to our blood and removing carbon dioxide that our cells have produced as metabolic waste. This precise ratio, maintained by an extraordinarily complex web of geological, biological, and chemical processes that took billions of years to develop and stabilize on Earth, is the chemical environment that every cell in your body is calibrated to. Change it significantly, and life as we know it cannot continue. The atmosphere of Kepler-452b is unknown in its precise composition. We have no direct measurements. No spacecraft has flown past it. No telescope has yet meaningfully pierced its clouds. The James Webb Space Telescope, humanity's most powerful space observatory, is theoretically capable of characterizing the atmospheres of some nearby exoplanets by studying the light that passes through those atmospheres during transits. But Kepler-452b is too far away, and its transit signal too faint for even JWST to make meaningful atmospheric measurements. We are working from models built from physics and chemistry and planetary science, extrapolated from the known properties of the planet and its star. And those models paint a portrait of an atmosphere that is, by any measure, profoundly hostile to human life. Let's start with carbon dioxide. Carbon dioxide is a trace gas in Earth's atmosphere today, comprising roughly 0.04% of the total atmospheric mix. Yet even this tiny fraction has a measurable greenhouse effect, and we know from Earth's own geological record that even modest changes in atmospheric CO2, on the scale of a few hundred parts per million, have driven dramatic climate shifts, ice ages, and warm periods throughout our planet's long history. At higher concentrations, CO2 is directly toxic to humans, independently of temperature effects. At about 1% concentration, which is 25 times its current level in Earth's atmosphere, humans begin to experience measurable cognitive impairment. Decision-making slows, attention narrows. At 4% concentration, breathing becomes labored and headaches set in rapidly. At 8 to 10%, unconsciousness follows within minutes, and death follows soon after if the person is not removed to breathable air. On a world with Kepler-452b's estimated properties, where volcanic outgassing is elevated, where the carbon silicate weathering cycle may be operating less efficiently than on Earth due to the possible stagnant lid tectonic regime we discussed earlier, and where the runaway greenhouse process may be accumulating CO2 faster than any geological process can sequester it. The atmospheric concentration of CO2 could be dramatically higher than anything Earth's biology could tolerate. The carbon silicate cycle deserves a clear explanation here, because it is the key mechanism that keeps Earth's atmospheric CO2 at levels compatible with life, and its potential disruption on Kepler-452b is critical to understanding what the atmosphere might be like. On Earth, carbon dioxide is continuously removed from the atmosphere by a geological and chemical process. Rain, which dissolves CO2 from the atmosphere to form weak carbonic acid, falls and chemically weathers silicate rocks at the surface. This weathering releases calcium and magnesium ions, which eventually wash into rivers and oceans. There, marine organisms use these dissolved minerals, along with dissolved CO2, to build shells and skeletons of calcium carbonate. When these organisms die, their shells sink to the ocean floor and are buried as limestone and related rocks, effectively locking atmospheric carbon dioxide into solid rock for millions of years. At subduction zones, these carbonate-rich rocks are eventually pulled back into the mantle, where at high temperatures and pressures they release CO2 back into the atmosphere through volcanic activity. This is the long-term carbon cycle. It is Earth's thermostat. It is what has kept our atmosphere stable enough for complex life for hundreds of millions of years, even as solar luminosity has increased and as massive volcanic events have periodically disrupted the system. It is fragile, but it works. On a stagnant-lid world like Kepler-452b may be, the subduction component of this cycle, where carbonate rocks are pulled back into the mantle for eventual re-release, may be severely limited or effectively absent. The geological recycling mechanism doesn't function. Carbon sequestered in ocean floor sediments may stay there, but as the oceans disappear due to the runaway greenhouse, even this pathway for CO2 removal closes off. Meanwhile, the ongoing volcanic release of CO2 continues without a compensating removal process. The net result is a gradual, potentially dramatic buildup of atmospheric carbon dioxide. Combined with the loss of water vapor through photodissociation as the greenhouse spiral progresses, the atmosphere of Kepler-452b may be moving toward a composition dominated by CO2, in concentrations that are directly and rapidly lethal to any life form using biochemistry similar to our own. Then there are the sulfur compounds, which cannot be ignored. Active volcanism on a super-Earth releases sulfur dioxide and hydrogen sulfide continuously. On Earth, these gases are diluted into a large, chemically buffered atmosphere and chemically neutralized by interaction with rainwater and surface minerals. On Kepler-452b, with higher volcanic activity and a less efficient carbon silicate cycle, sulfur compound concentrations in the lower atmosphere could be high enough to be independently toxic, even before we account for the carbon dioxide levels building above them. Sulfur dioxide in the atmosphere reacts with water vapor to form sulfuric acid aerosols. Even in small concentrations, sulfuric acid mist causes severe chemical burns to the respiratory tract, progressive scarring of lung tissue, and acute respiratory distress. In higher concentrations, it causes immediate incapacitation. Combined with the already elevated atmospheric pressure, the high CO2 concentrations, and the physical demands of breathing under 2G gravity, the respiratory system of any unprotected human on Kepler-452b would be under assault from multiple directions simultaneously, the moment any suit seal was compromised. And then there's the matter of oxygen itself. For Kepler-452b to have atmospheric oxygen at levels that support human breathing, something would need to be continuously generating it. On Earth, free oxygen in the atmosphere is almost entirely a biological product, produced by photosynthetic organisms, first ancient cyanobacteria and later plants, as a byproduct of splitting water molecules during photosynthesis. Before the rise of widespread photosynthesis roughly 2.4 billion years ago, in what's called the Great Oxidation Event, Earth's atmosphere had virtually no free oxygen. The breathable air we take for granted is, in a profound sense, the accumulated exhaust of billions of years of biological productivity. For Kepler-452b to have breathable oxygen levels today, given the ongoing runaway greenhouse effect, and the likely hostile surface conditions, it would require either a thriving globally active biosphere, engaged in massive photosynthesis in conditions that seem increasingly hostile to complex life, or some non-biological oxygen production mechanism of extraordinary and implausible efficiency. Neither seems particularly compatible with everything else the planetary models tell us about the current state of this world. In all probability, the air of Kepler-452b contains very little to no free oxygen. What all of this adds up to is an atmosphere that requires sophisticated, robust, permanently maintained life support systems simply to survive from one moment to the next. Not for a few hours, as astronauts use during spacewalks, not for a day or a week, but continuously for every hour of every day of your life on this world. A breach in your suit's seal, a failure in your habitat's air recycling system, a moment of unprotected exposure to the outside environment, any of these would be rapidly and irreversibly fatal. Space agencies routinely emphasize the extraordinary complexity and cost of maintaining life support for astronauts on the International Space Station, which orbits only 400 kilometers above Earth's surface and can be resupplied from the ground within hours if a critical system fails. The redundancy systems required are already among the most complex and carefully engineered assemblies humanity has ever created. Now imagine maintaining those systems on a world where resupply from Earth requires a minimum of 1,400 years of travel time, where the nearest equivalent of a spare parts warehouse is 1,400 light-years away, and where every component of your life support system degrades over time in an environment whose chemistry is actively trying to corrode it. The atmosphere of Kepler-452b is not simply an inconvenience or a technical challenge. It is an existential daily threat, a continuous, unrelenting hazard that would demand technological solutions of a sophistication and reliability that no human engineering has yet come close to achieving over the timescales a permanent colony would need. Here's your question for this section. Think about what it would mean for life support technology to be as reliable and self-sufficient as the planet's natural environment is for us here on Earth. Do you think artificial intelligence and autonomous robotic repair systems could ever be trusted to maintain a sealed life support environment with the kind of reliability needed for permanent settlement on a world like Kepler-452b? Or is there a fundamental limitation in trusting machines with the only thing standing between you and a lethal atmosphere? Let me know in the comments. So we've established that Kepler-452b is hostile to human survival in nearly every physical dimension we've examined. The gravity crushes steadily and relentlessly. The air chokes and corrodes. The volcanoes rumble beneath unstable ground. The star burns too hot and too bright. The greenhouse effect spirals upward with no equilibrium in sight. But here's where the story takes an even more philosophically unsettling turn. None of what we've described is new. None of it appeared last week, or last century, or last million years. This world has been building its particular suite of hostilities for billions of years, which raises a question that, once you hear it clearly, is very difficult to stop thinking about. If Kepler-452b has been sitting in the habitable zone of a stable, sun-like star for 6 billion years, longer than complex life has existed on Earth, then where is everybody? The search for extraterrestrial intelligence. SETI. It is one of the most profound, most audacious, and most philosophically consequential scientific projects in human history, and also, arguably, one of the loneliest. For over 60 years, we have been pointing enormous radio telescopes at the sky, listening. Patiently, systematically searching through the electromagnetic noise of the cosmos for a signal that carries the unmistakable signature of intentional transmission. A signal that says, Simply and unmistakably, we are here. We exist. We have thought long enough and built sophisticated enough instruments to send a message into the dark between stars. The science behind this search is built on sound reasoning. If an intelligent civilization exists somewhere in the galaxy and has developed technology at least comparable to our own, they would almost certainly be generating electromagnetic radiation. Radio waves, television broadcasts, radar systems, deliberate interstellar transmissions, all of these would leak into space and, in principle, be detectable from significant distances by a sufficiently sensitive receiving instrument. We know this because Earth itself has been broadcasting its electromagnetic signature into space for over a century. The expanding sphere of our radio emissions now extends roughly 100 light-years from Earth in every direction, and any civilization within that distance with technology comparable to our own could, in principle, detect it. The SETI Institute, based in California, operates the Allen Telescope Array in the mountains of Northern California, an array of individual radio dishes working in concert to survey large portions of the sky simultaneously across a broad range of frequencies. In the years following the discovery of Kepler-452b in 2015, the Allen Telescope Array specifically and deliberately targeted the Kepler star system in the constellation Cygnus. The researchers listened across a wide range of radio frequencies, including the frequency range considered most likely for deliberate interstellar communication. They applied sophisticated signal processing algorithms designed to distinguish artificial signals, with their characteristic narrow bandwidth and structured patterns, from pulsars, from quasars, from the complex natural electromagnetic background noise of the galaxy. The result, when it came, was the same result that has greeted every SETI search in 6 decades of listening: silence, total, absolute, unbroken silence. No signal, no whisper, no technological fingerprint, no evidence of any civilization, present or past, broadcasting from the direction of Kepler-452b. Now, before we read too much into this silence, it's important to acknowledge honestly what it does and doesn't tell us. Kepler-452b is 1,400 light-years away. Any radio signal from a civilization at our current level of technological development, broadcasting with our current signal strengths in all directions rather than deliberately targeting us with a focused transmission, would be so diluted over that distance as to be essentially undetectable by any instrument we currently have. Our radio bubble, the expanding sphere of electromagnetic radiation from Earth, is 100 light-years in radius. At 1,400 light-years, the signal from Earth's 20th century broadcasts would be indistinguishable from background cosmic noise, even for a civilization using telescopes far larger and more sensitive than anything we've built. So the absence of detected signals does not definitively mean there's no one at Kepler-452b. It might simply mean the distance is too great for our current instruments to pick up ordinary technological leakage at that range. However, the silence becomes far more interesting and far more pointed when you consider the context and the timescales involved. Kepler-452b orbits in a solar system that has had 6 billion years of relative stellar stability, 6 billion years of a consistent, warm, benign energy source. For reference, life on Earth appeared relatively quickly, within the first few 100 million years of Earth's formation. Complex, multicellular life appeared roughly 540 million years ago. Tool-using intelligence appeared roughly 300,000 years ago. A technological civilization capable of radio transmission appeared roughly 100 years ago. If we assume following Earth's trajectory as our only example that intelligent life tends to take on the order of a few billion years to develop from the chemistry of life to the technology of radio transmission, then any civilization on Kepler-452b would have reached our current technological level somewhere between 1 and 2 billion years ago. 1 to 2 billion years ago. And here is the part that deserves a slow, quiet pause. In 1 to 2 billion years, a civilization with the same initial trajectory as ours could have progressed so far beyond our current state that the comparison simply defies imagination. We have only been a technological civilization for approximately 100 years. In 1 to 2 billion years, extrapolating the exponential growth curve of human technology, the changes would be as incomprehensible to us as modern computers and smartphones would be to an ancient cave dweller. A civilization that old should, by reasonable extrapolation of the exponential growth of technology, have exhausted its home planet's resources and moved outward, should have colonized its solar system, should have begun, billions of years ago, colonizing neighboring star systems, should be, by now, if it followed any path remotely like our own developmental trajectory, leaving its signature written across the structure of the galaxy itself. Physicist Nikolai Kardashev developed a classification scale for civilizations based on their energy usage. A Type 1 civilization controls the full energy resources of its entire home planet. A Type 2 civilization controls the full energy of its entire star. A Type 3 civilization controls the energy of its entire galaxy. Humanity today is estimated to be at roughly 0.7 on the Kardashev scale. We are below Type 1. A civilization starting from Kepler-452b's position, 1 to 2 billion years ago, should, by almost any physical or engineering argument, have reached Type 2 status long before now. A Type 2 civilization would be visible to us through the megastructure scale modifications it made to its own star's energy output, what are called Dyson sphere signatures, vast engineering projects designed to capture the full output of a star. These would produce specific, detectable infrared signatures. We see none of this from Kepler-452b's direction. No anomalous stellar signatures. No megastructure scale infrared emissions, no structured electromagnetic signals, no evidence of coordinated stellar engineering, no radio transmissions of any power level we can detect at this distance. The silence is not just the absence of a radio whisper. It is the absence of any signature of a civilization that should, if it followed a path anything remotely like our own, be by now almost cosmically visible. This is the heart of the Fermi paradox, that famous question posed by physicist Enrico Fermi in 1950 during a lunch conversation at Los Alamos. Where is everybody? Given the age of the galaxy and the probable prevalence of habitable planets, the universe should be, by most estimates, teeming with evidence of intelligent life. And yet, looking in every direction we've examined with every instrument we've built, we detect nothing. Nothing coordinated, nothing artificial, nothing unmistakably intentional. For Kepler-452b specifically, the silence is especially pointed because this is not a poorly characterized system of unknown age or unknown stellar type. This is a well-studied star of a precisely known age, around which a likely rocky planet orbits in the habitable zone. The conditions are as promising as any we've found, and the timescales available for the development of life and intelligence are more generous than anywhere else we've closely examined. And yet, silence. Here's the question I want you to consider carefully and comment on below. When you think about the silence of SETI searches like the one targeting Kepler-452b, which explanation resonates most deeply with you? Do you think intelligent life is genuinely rare in the cosmos, rare enough that we might be alone in the observable universe? Or do you think we're simply looking in the wrong ways, with the wrong instruments for the wrong signatures? What's your best theory for the great silence? I want to read every theory you have. The silence from SETI is haunting on its own terms. But there's another possibility that in some ways is even more profoundly haunting. Not that intelligent life never existed on Kepler-452b, but that it did, that it flourished, perhaps for billions of years, and that it had to leave. Consider a thought experiment. You are a planetary scientist, and you've just been handed complete knowledge of Kepler-452b's history. Not the observational data we have today, but the full geological and biological record of the planet across its entire 6 billion-year lifespan. You scroll through it like a film in fast forward. Life appears relatively early in the warm chemistry of shallow seas during the planet's first billion years. Single-celled organisms. Then, over the following hundreds of millions of years, increasing complexity. Multicellular organisms. Then animals. Then intelligence. Then something that looks, from a geological record standpoint, like the signature of technology. Unusual mineral deposits. Atmospheric chemical anomalies consistent with industrial activity. The traces of a civilization building, manufacturing, changing its own atmosphere. And then, at a certain point in the geological record, something changes. The star above keeps brightening. The climate begins to shift. The once comfortable surface temperatures begin to climb. And then the signatures change again. New ones. Atmospheric compositions shifting in ways that suggest deliberate engineering, an attempt to counteract the warming. And then, at some point, those signatures thin and fade. And then silence. What happened? This is the civilization migration hypothesis, a concept that emerges from taking the Fermi paradox seriously in the context of old, inner-edge habitable zone planets like Kepler-452b. The hypothesis proposes a simple and quietly devastating explanation for why such planets might be silent. Any civilization that developed there was forced out by the brightening star. The logic runs like this. The warming of Kepler-452b by its aging star has not been a sudden event. It has been gradual, astronomically predictable. The kind of change that shows up clearly in long-term climate data, in increasingly warm average temperatures, in the slow recession of coastlines, in the bleaching and disappearance of complex ecosystems. Any civilization advanced enough to understand stellar physics, a milestone our own civilization reached within a century of the Industrial Revolution, would have seen this coming with hundreds of thousands, if not millions, of years of warning. And a civilization with that much warning time and a billion years of technological development behind it would have had options we can barely imagine. The first option would be planetary engineering, deliberate, large-scale climate intervention to counteract the solar brightening. Deploying enormous reflective structures in orbit to redirect incoming energy back to space. Manipulating atmospheric composition to actively reduce the greenhouse effect rather than allowing it to build. These are ideas that our own civilization now discusses in early theoretical terms as potential responses to our own climate situation. For a civilization with 1 billion years more technology and 1 million years of warning time, the execution of such a plan would be not a science fiction dream but a practical engineering project. If they tried and succeeded, they might still be there, hidden from our view by the mundane character of a planet that hasn't changed in obvious ways because they prevented the change. Silent not because they don't exist, but because they've evolved beyond the radio frequency emissions that we're searching for. If they tried and failed, they faced the remaining option: migration. Not migration across a continent or an ocean or even a planet. Migration across space. Departure from the home world to somewhere else in their solar system or somewhere else in the galaxy entirely. Now, the practical challenges of such a migration from a planet with 2G surface gravity are significant, even for an enormously advanced civilization. Launching large numbers of physical beings off the surface of Kepler-452b faces the same escape velocity constraints we discussed earlier. But a civilization with 1 billion years of technological development would not be facing this problem in the way our current civilization would face it. Their relationship with energy, materials, and propulsion would be as alien to us as our current technology would be to a person from ancient Egypt. One possibility is that the migration wasn't a sudden, emergency evacuation. It might have been a centuries-long, carefully planned population shift. The civilization may have established off-world habitats in their solar system, on moons, on space stations, in asteroid colonies, long before the planetary crisis forced a final departure from the home world. The last inhabitants to leave the planet might have been a small group of holdouts, maintaining the home world for historical or sentimental reasons long after the main population had already moved elsewhere. Or perhaps the civilization's relationship with biology itself had changed fundamentally by the time the migration became necessary. Through genetic engineering, or through the transfer of consciousness to digital substrates, or through forms of existence that our current neuroscience and philosophy haven't yet conceived of. The physical challenges of leaving a high-gravity world may have ceased to apply to them in the way they would apply to us today. The question of where they would have gone is equally fascinating and equally unanswerable from our current vantage point. Our galaxy contains hundreds of billions of stars. Among these, there are enormous numbers of stellar systems with potentially habitable planets or moons. For a civilization advanced enough to have survived on a changing world for billions of years, identifying and reaching a new habitable environment would presumably be solvable, however challenging the journey, if they migrated within their own solar system. To a moon of an outer gas giant where conditions might be more stable, or to an engineered habitat beyond the reach of their brightening star's influence, they might still be in the same stellar system, but impossible to detect from our current distance and with our current instruments. If they migrated to another star system, they chose a destination we have no way of predicting, and their new home might be anywhere in the galaxy, anywhere among hundreds of billions of possible stellar addresses. There is, of course, another possibility that is perhaps the most sobering of all. What if they didn't make it? What if the planetary change outpaced even their ability to respond? What if, despite billions of years of civilization and millions of years of warning, the sheer scale of the geological and atmospheric transformation required the mobilization of resources beyond what their civilization could sustain under the increasingly hostile surface conditions? What if disease or internal conflict, or the cascading failures of a civilization under existential stress, prevented the successful execution of a migration that was, in principle, theoretically achievable? The geological record of their existence would remain on the planet below. Not radio signals, not electromagnetic emissions, but rock. The compressed and eroded remnants of foundations, built from unusual alloys or composites. The chemical traces of industrial processes, preserved in ancient sediment layers that a future geologist might one day sample and analyze. Perhaps even biological remains, preserved in the right geological conditions, yielding genetic information about beings that thought and built and wondered about the stars just as we do. But from 1,400 light-years away, with current technology, we cannot search the rock. We cannot analyze the sediment from this distance. We cannot look for the chemical fingerprints of an ancient industrial civilization in the geological layers of a world we've never visited and may never visit. We can only listen to the radio spectrum and look at the silhouette of the planet as it passes in front of its star, and neither of these tells us what's written in the stone below. The desolate relic idea is perhaps the most emotionally resonant interpretation of Kepler-452b's silence. Under this framework, The planet we've been discussing tonight is not a world waiting to be discovered and colonized. It is an abandoned one. The geological processes have continued for hundreds of millions of years, since whatever civilization existed there last left any trace on the surface, eroding and overriding any obvious remnants of their presence. The planet has moved on, as planets do, indifferent to the civilizations that rose and fell in the thin chemical layer of its surface. You wouldn't be arriving on a new frontier. You would be arriving on the picked-over ruins of an ancient world. A world that ran out of time. And if you were to walk across its surface under its gray-white sky, through its toxic pressurized air under the weight of twice the gravity you were born into, you would have no way of knowing whether the rock beneath your boots was ordinary untouched stone, or the eroded remnant of a road or a plaza, or a foundation laid by minds that looked up at their brightening star with the same mixture of wonder and dread that we now look up at the sky and see the future of our own world written in the stars around us. That not knowing is, in some ways, the most profound silence of all. Here's the thought I want to leave with you for this section. If an intelligent civilization once existed on Kepler-452b and was forced to migrate, do you think they would have left behind any kind of message for civilizations that might come after them? A marker, a beacon, a time capsule encoded in the geology of the planet itself? And if they did, would we even know what to look for? Do we currently have, or could we develop, the scientific tools to distinguish a deliberate alien artifact from an unusual rock formation? Share your thoughts below. This is one of those questions that genuinely keep some astronomers awake at night. We've been building a portrait of Kepler-452b as a world under siege from above, from the brightening star, from the runaway greenhouse, from the thickening toxic atmosphere. But there's one final physical mystery about this world that calls all of our assumptions into question from a completely different angle. What if the clouds above Kepler-452b, those dense, planet-wide, suffocating clouds that we've been picturing as heavy with moisture and heat, what if they're not made of water at all? What if this world has always been dry? What if it never had the ingredient that we consider the most fundamental prerequisite for life as we know it? Water is so fundamental to our concept of habitability that we've built entire scientific frameworks around its presence. The habitable zone is sometimes called the liquid water zone, defined specifically as the range of orbital distances at which liquid water can exist on a planet's surface. The phrase "follow the water" has become something of a guiding mantra in the search for life beyond Earth, driving the priorities of astrobiology missions from Mars to Europa to Enceladus and beyond. We look for water because every single life form we have ever discovered, every organism we've studied, every biochemical system we've characterized uses liquid water as its essential solvent. The biochemistry of life, the dissolving of nutrients, the transport of molecules within cells, the facilitation of enzymatic reactions, the maintenance of the cellular structures that make self-replication possible, all of it happens in water. Water is not just a habitat preference or a convenience. It is, as far as everything we understand about biochemistry tells us, a fundamental necessity for life as we know it. And so when we imagine Kepler-452b sitting in the habitable zone of a sun-like star with an orbital period similar to Earth's, we have instinctively and almost unconsciously imagined a wet world. Blue oceans, rainfall, clouds of water vapor arching over a moist, living surface. A planet where liquid water is freely available for the chemistry of life to begin and flourish. But what if that assumption is wrong? Here is the critical point. The presence of a planet in the habitable zone tells us only that, given certain atmospheric assumptions, liquid water could exist on the surface if water were present. It says nothing at all about whether water was ever delivered to the planet in the first place. Habitability and water availability are related but independent questions. Water is not automatically present on rocky planets in the inner regions of solar systems. During planet formation, the inner region of a protoplanetary disk, close to the young star where temperatures during formation are elevated, tends to be too warm for water ice to condense and be incorporated directly into the solid rocky bodies forming there. Earth itself appears to have received a substantial portion of its water, not from its original formation material in the hot inner disk, but from the outer solar system, delivered over millions of years by a specific mechanism. The mechanism by which Earth received this water is not just fascinating. It is directly relevant to understanding the water budget of Kepler-452b. In our early solar system, the region beyond roughly what is now the asteroid belt was cold enough for water ice to condense and become part of the solid material forming asteroids, comets, and other small bodies. These ice-rich bodies originally had orbits confined to the outer solar system, well away from the warm inner planets. But Jupiter changed everything. Jupiter, the largest planet in our solar system, has a gravitational field of enormous reach and influence. As Jupiter formed and settled into its current orbital position, its gravity began interacting dynamically with the orbits of countless smaller bodies in the outer solar system, deflecting them, scattering them, and in a significant fraction of cases sending them on trajectories that plunged into the inner solar system. A fraction of these gravitationally deflected bodies, asteroids and comets rich in water ice and hydrated minerals, struck the inner rocky planets, including Earth, during a period called the Late Heavy Bombardment, roughly 4 billion years ago. This delivery mechanism is believed to be responsible for a significant portion of Earth's water budget. Some estimates suggest that half or more of Earth's surface water may have arrived this way, courtesy of Jupiter's gravity acting as a cosmic slingshot for water-rich outer solar system material. Without Jupiter, the inner solar system, including Earth, may have been substantially drier, possibly dramatically drier. This is called the Jupiter effect in the context of planetary habitability, and its implications extend far beyond our own solar system to every planetary system we discover. For Kepler-452b to have received substantial water through the same mechanism, its solar system would need to have contained a planet of Jupiter's mass and general orbital character, large enough to gravitationally scatter ice-rich outer solar system bodies into the inner system, where Kepler-452b orbits. We have no observational evidence of such a planet in the Kepler system. The Kepler Space Telescope's primary detection method, the transit technique, is sensitive mainly to planets whose orbits are aligned such that they pass in front of their star from our vantage point. While Kepler-452b was detected this way, the absence of other detected planets doesn't definitively prove the system has no other worlds. A Jupiter-mass planet in a larger, differently inclined orbit might simply not produce transits visible from Earth, or might have an orbital period too long for Kepler to detect in its observation window. But neither do we have evidence that such a planet exists in this system. The water delivery history of Kepler-452b is genuinely, substantially unknown, and this uncertainty opens a disturbing possibility that changes everything else about our picture of this world. If Kepler-452b formed in the inner habitable zone of its star, without the gravitational influence of a Jupiter-scale companion to deflect water-rich outer solar system bodies toward it, the planet may have formed nearly dry. Not completely water-free, perhaps. Some water would have been incorporated into the minerals of the rocky bodies that eventually accreted to form the planet, and released later through volcanic outgassing into the early atmosphere. But the amount of water delivered by this mechanism alone is relatively modest compared to the deep, planet-spanning oceans of Earth. It might produce shallow seas, or scattered lakes, or subsurface ice deposits, rather than the deep, globally distributed liquid water ocean that Earth's geology suggests came largely from outer solar system delivery. A dry or near-dry Kepler-452b would look very different from the water-rich world we've been imagining throughout this journey. The thick clouds we discussed earlier, that planet-wide, oppressive ceiling of gray-white clouds stretching horizon to horizon, might not be water clouds at all. On a dry, volcanically hyperactive world with a CO2-rich, warming atmosphere, clouds can form from very different and very unpleasant materials. Sulfur dioxide from volcanic outgassing combines with even modest amounts of water vapor to form sulfuric acid aerosols. These aerosols nucleate clouds. Venus, as we've discussed, has planet-wide cloud cover composed primarily of sulfuric acid droplets, and this cloud system reflects approximately 70% of incoming sunlight back into space, giving Venus its familiar bright, creamy appearance in our night sky. From a distance, Venus's cloud cover looks to an uninformed observer like an ordinary, perhaps heavy cloud deck. It is not. It is a planet-spanning curtain of corrosive acid. On Kepler-452b, without sufficient liquid water to maintain an efficient carbon cycle or to sustain the chemistry of silicate weathering, the atmosphere would likely build toward a thick, CO2-dominated, high-pressure environment even faster than the greenhouse arguments alone would suggest. The clouds above Kepler-452b might be composed of sulfuric acid aerosols, carbon dioxide ice crystals at high altitudes, and mineral dust lofted from a geologically active surface, not water. And this has profound implications for the one thing that underlies every other argument for Kepler-452b as a potentially habitable world. Life. Every step of the biological possibility argument for Kepler-452b has implicitly assumed the presence of liquid water. Remove the water, and the foundation of the biological possibility disappears entirely. The habitable zone only means something biologically if there's water to be liquid within it. A planet in the habitable zone without water is not a potentially habitable planet. It is simply a warm rock. A dry Kepler-452b would not just be lifeless. It would be lifeless in a deeper, more fundamental sense than a warm, wet world devastated by a runaway greenhouse effect. A runaway greenhouse world at least had liquid water in its early history, and that early history is where the window for life would have been. A dry world never had that window at all, not in any form we currently know how to recognize as life-supporting. This interpretation also reframes the silence of SETI in a new and simpler light. The silence might not be the aftermath of a civilization that once thrived and then migrated or perished. It might be the silence of a world that was never hospitable to the kind of chemistry that produces life. A world that was always, from its very earliest formation billions of years ago, a beautiful, interesting, geologically dynamic, scientifically fascinating, and utterly sterile rock. The missing water mystery is ultimately a reminder of something important. The presence of a planet in the habitable zone is a necessary but deeply insufficient condition for habitability. A world must also receive water in sufficient quantity. It must have the geological and chemical machinery to maintain water in liquid form over geological timescales. It must have the atmospheric balance to prevent either freezing or boiling away the water once received. It must maintain all of these conditions simultaneously and continuously long enough for life to arise, establish itself, grow complex, and perhaps develop the kind of intelligence that looks back up at the stars with wonder. Each of these requirements may seem individually achievable, but requirements stack. and the intersection of all of them, in the right combination for long enough, may be rarer and more precious than our hopeful early estimates of galactic habitation imagined. Here's your question for this section. The follow the water principle is the cornerstone of how we currently search for life in the cosmos. But what if life doesn't require water specifically? What if there are forms of life we cannot currently imagine, using different solvents, different biochemistries, different fundamental organizing principles? Does the possibility of genuinely alien biochemistry change how you think about the search for life beyond Earth? And should we be devoting more resources to looking for that kind of life? Leave your thoughts below. We've traveled far together tonight. From the hopeful early headlines of 2015 to the cold, unforgiving physics of a world that invited our dreams and then handed us a masterclass in reality. We've felt the gravity bearing down. We've breathed the choking, toxic air through our imaginations. We've watched the oceans slowly thin and evaporate. We've listened to the silence that comes from a direction in the sky, where a civilization should have been shouting its existence to the cosmos. And we've sat with the terrifying and poignant possibility that whoever, or whatever, was there before us has already moved on, been silenced, or simply never existed in the form we hope to find. It's time to come home. As we slowly pull away from Kepler-452b, rising up through its oppressive, thick cloud ceiling, through its toxic atmospheric layers, through the brightening glow of its aging star, and out at last into the cold, silent clarity of interstellar space, let's look back at what we found. Not a paradise. Not an escape. Not a twin. What we found across 1,400 light-years of void is a mirror. Kepler-452b is, in every measurable dimension we've examined tonight, a warning. A message written not in language but in the universal language of astrophysics and planetary science, sent to us across the light years in the form of photons and orbital mechanics and spectroscopic inference. And the message, when you decode it through everything we've discussed, reads something like this. Time is not infinite. Stars age. Planets change. The conditions that make a world habitable are fragile, temporary, and impermanent on the timescales of the cosmos. The window during which a rocky planet orbiting a sun-like star can support liquid water, and the chemistry of life is long in human terms, measured in the billions of years, but brief in cosmic ones. And when that window closes, it closes finally, completely, and without appeal. Our own sun is a middle-aged star. It has been burning for 4.6 billion years, and it has roughly another 5 billion years of its main hydrogen-burning phase remaining before it begins its dramatic final transformation. During those remaining billions of years, it will continue to gradually brighten. Models suggest that within roughly 1 billion to 1.5 billion years from now, the increasing solar luminosity will begin to push Earth uncomfortably warm. Within 1 billion years after that, the moist greenhouse effect may begin on Earth itself. The oceans may begin to thin at the edges. The carbon cycle may begin to weaken as silicate weathering slows in a warming world. The planet's long era of rich, diverse, abundant biological life may begin, slowly and irreversibly, to fade. These timescales are so large as to be essentially meaningless to any individual human life, to any particular human civilization, to any institution we've ever built. 1 billion years from now, nothing that we call civilization today will still exist in any recognizable form, regardless of what Earth's climate does. We will have changed, evolved, or disappeared long before the solar brightening becomes a crisis. But these timescales are not meaningless to the concept of humanity as a long-term presence in the cosmos. They are not meaningless to the question of what kind of relationship we build with the universe and with our own world over the centuries and millennia that lie ahead of us. Kepler-452b is showing us what happens when a planet reaches the inner edge of its habitable zone. We don't know for certain what happened there. We don't know if life ever arose from its early chemistry. We don't know if intelligence ever developed from that life, or if civilization ever flourished and sang its brief songs into the cosmic quiet before going silent. We only know the outcome, a world that is, by all current indications, in the process of becoming uninhabitable, slowly, methodically, on geological timescales, unstoppably. Our own planet is on the same trajectory. The stellar type is the same classification. The mechanism is the same brightening of an aging main sequence star. The eventual outcome, barring some intervention we cannot currently conceptualize, is the same loss of surface water and the same collapse of the carbon cycle. The only difference between Earth today and Kepler-452b today is time. And approximately 1.4 billion years of it. 1.4 billion years is an almost incomprehensible amount of time. It is enough time for the evolutionary history of Earth from its simplest multicellular organisms to repeat itself roughly 4 times. It is enough time for our Sun to complete more than a quarter of its remaining main sequence life. It is enough time for civilizations beyond anything we currently imagine to rise, flourish, struggle with the same existential questions we're asking tonight, and either find a way forward or run out of road. We have time. More time, in fact, than we can meaningfully reason about in the currency of human experience. But time has direction. Time moves in only one direction. And the direction it moves in, for any planet orbiting a main sequence star, is toward a warmer, brighter star, and eventually toward the end of the conditions that make complex life possible. Kepler-452b is showing us the direction of that arrow. It is showing us, across 1,400 light-years of space, what Earth is pointed toward in the deep future. It is, in the most profound sense possible, a mirror held up by the cosmos, reflecting back to us not who we are now, but what our world will look like after another 1.5 billion years of starlight. And if there is any wisdom to be extracted from this beautiful, terrible, scientifically astonishing world, it is this: Earth is precious, not in a sentimental way, not in the way that people say their hometown is precious because they grew up there, precious in a hard, physical, scientific sense. Precious because the conditions that make it habitable, the right orbital distance from a star of the right age, the presence of vast liquid oceans, the efficient operation of the carbon silicate cycle, the nitrogen-oxygen atmosphere maintained by billions of years of biological productivity. The single G of gravity that our bones and our hearts and our blood were built for, these conditions are not guaranteed. They are not permanent. They are not waiting for us whenever we decide to take them seriously. They are here now. They are working now. And they will work for approximately 1 billion more years before the forces that are already transforming Kepler-452b begin to transform our own world in the same slow, planetary scale way. So the next time you step outside and feel the weight of the Earth's gravity holding your feet gently, naturally, effortlessly to the ground, the weight that your bones and your heart and your blood vessels were built to bear across hundreds of millions of years of evolution, remember what 2G feels like. Remember what it does to a heart over years. Remember what it does to a spine, to joints, to the simple act of lifting your arm to reach for something. And then breathe. Breathe the air that is freely given to you, mixed at the right ratios, pressurized at the right level, at the right temperature, by a planet and a biosphere that has been perfecting those conditions for billions of years quietly and without any fanfare, in preparation for you and for every living thing that came before you. The cosmos is vast. It is endlessly, almost incomprehensibly interesting. It is filled with worlds we haven't found yet, with physics we don't yet understand, with the possibility of discovery and understanding that stretches farther than our imaginations can currently reach. And somewhere out there, beyond the 1400 light-years that separate us from Kepler-452b, beyond the familiar stars of our own stellar neighborhood, there may be worlds that are genuinely habitable, genuinely welcoming, genuinely hospitable to life in ways that Kepler-452b has ceased, or perhaps never managed, to be. We should keep looking for them. We should keep reaching. The impulse to explore, to seek beyond the comfortable and the familiar and the known, is one of the finest and most enduring things about us as a species. It has carried us from caves to cathedrals to orbital space stations. It will, one day, carry us to the stars. But perhaps the stars are not meant to be conquered as quickly as our ambition sometimes demands. Perhaps they are meant to teach us, to humble us, to challenge our assumptions about what is common and what is rare and what is irreplaceable. Kepler-452b, that distant gray world crushed by its own gravity and slowly strangled by its aging star, teaches us something that no amount of optimistic astronomical press releases can ever teach quite so forcefully. Home is not everywhere. Home is not easily duplicated. Home is not waiting for us in the habitable zone of every sun-like star we find. Home is here. One gravity, breathable air, liquid oceans that haven't yet begun to boil, a star that has not yet grown too bright. This is the gift that Kepler-452b, in all its hostility and all its strangeness and all its haunting cosmic silence, gives us. It tells us what we have. Sleep well, travelers of the dark. The stars will still be there when you wake. They have been there for billions of years, and they will wait patiently for you. And when the morning comes, and the light of our own sun, gentle and exactly as bright as a healthy middle-aged star ought to be, falls across wherever you rest, remember that this light is not guaranteed. Remember that it is borrowed. Remember that it is, on the timescales of the cosmos, brief. And let that knowledge make this morning, this air, this gravity, this particular improbable beautiful place in space and time, feel a little more extraordinary than it did yesterday. The ground beneath your feet is still here, at exactly one gravity, exactly as it should be.